And recording now. Well, where we left off last time, talking about transaction structures, just the idea that transactions follow this kind of request agreement sequence, that the user wants to do something, tries to do it, the system either lets the user do it or doesn't. Okay, and basically there's a step-by-step process where you make sure that things happen in the correct order. Otherwise, you have to go back and restore your database to some earlier state, which is usually a problem. Okay, so two basic models. Number one, you can think about banking as an archetype. In a banking system, customers are isolated, right? You don't have customers typically sharing access to the same data. It's possible, but the likelihood is pretty low and it's not typical. So you can watch for when it happens, but it's not something you have to constantly keep track of. Okay, the exception to that, to some extent, is the idea that customer transactions impact the bank reserves. Banks have to keep a certain amount of assets on hand so that they can pay out customers. There's a legal requirement to do that. And of course, every time customers take money out of the bank, it's going to affect those reserves. Retail, on the other hand, in retail, it's entirely routine for customers to share access to inventory. Think about a bunch of customers randoming around the same store. It's entirely possible that two customers could see the same product on a shelf, reach for it at the same time. Well, same thing with a website. Two customers could be looking at the same web page at the same time and potentially buy the same last item. So the store needs some kind of policy to prevent multiple customers from claiming the same item or otherwise overdrawing from inventory. Typically, there's something like airplane seat reservations. You want a seat, somebody else wants the same seat. The airline's got to make some way where one or the other of you gets it. You can't both have it. And because of that, the transaction models are going to be different. So in a banking system, it's going to be different from a retail system. All right. So the key issue there, something called concurrency. Concurrency is when two users attempt to change or otherwise access the same data at the same time. Now, a business has to come up with some kind of policy addressing concurrency. One possibility is to be super strict and not to allow any simultaneous access to the same data. This sounds nice, but it's not always feasible. Imagine if you're on Facebook and you're looking at somebody's page. If you absolutely said, no, there's no simultaneous access to data, that means as long as you're looking at someone's profile page, nobody else can show up and look at that profile page, right? You don't necessarily want that. Or if somebody is looking at the comments on an article, nobody else can look at the comments on the article. Generally, in large-scale systems, especially where people expect real-time actions, this sort of prohibiting simultaneous access isn't really feasible. So, as a fallback, you might say, well, okay, any number of users can read the same data at the same time. As long as you're just looking at the data, that's not a problem, right? Any number of eyeballs can be looking at the data. Problem is when somebody wants to change it. So one possibility is just to say no changes are permitted if there's more than one viewer. Okay, this is something that might be feasible for a banking application. You say, okay, multiple people can look at your account details at the same time, but as long as there are multiple people logged into that account, you can't make any changes. Another possibility is allowing changes if there's multiple viewers, but those changes have to be immediately updated for all viewers. And this is typically what Facebook tries to do. For example, if one person likes a photo, then that like gets echoed to other replicas of that photo. So typically this is what the big systems do. They permit changes, but they try to update those changes to all users reasonably quickly. Okay, so in Facebook, the cost of damage is pretty low. If multiple people don't see the exact same set of likes on a photo for a minute, yeah, it's not a big deal. On the other hand, banking applications, financial applications generally, it can be a big problem if you allow changes. Even if you say, well, we're going to try to get them out quickly because maybe your system gets the changes out in milliseconds, but the users have somehow figured out a way that they can impose changes in microseconds, like in that Bitcoin hack. So it's an interesting policy question. The big factors driving it, number one, how many users there are and how often simultaneous access. So if you have a lot of users, well, simultaneous access is probably going to be inevitable. But if you don't, in fact, observe simultaneous access very often, it's maybe okay to be pretty strict about it. You can say, this is not a problem that's going to affect many users. Sure, you have to wait a while when it happens, but it's unusual. So maybe you decide to err on the side of caution. Another issue is system complexity. If you have a very complex system, you might not fully understand all the possibilities. In general, people try to make systems secure, but there are all kinds of vulnerabilities in there because it's difficult to cover every possible case. The more complex a system gets, the more it makes sense to be cautious and restrict the amount of simultaneous access. But the big one is simply the importance of data integrity versus the importance of response time. If you allow concurrent access to data, generally people are going to be able to complete their actions faster, and that'll make them happier. So that's a nice thing. Data integrity is also obviously a nice thing, right? That the data should always be correct. But some data integrity isn't that important, like who liked what Facebook photo, especially if you can catch up, a minute later and it'll all get sorted out. On the other hand, financials, like if you're doing big wire transfers of money, yeah, the data integrity is very important there, and the response time, people probably just have to wait. It's pretty typical for wire transfers that you might reserve a transaction time the following day, for example, just so that people have time to back out of it or verify that the transfer is in fact correct and not some bad guy trying to steal money out of your account. So concurrency, yeah, it's an interesting thing. It has some good features, it has some bad features, and businesses have to allow the amount of concurrency that makes sense. Okay, so in terms of transactions, we have a few related properties, some of which we've seen before. Okay, so again, we have atomicity, isolation, concurrency, right? We'll talk about those. So atomicity, again, means that a group of related tasks for a transaction is either entirely completed or not at all, right? In the specific case of transaction processing systems, the related tasks are things like the credit card getting processed, the inventory system getting updated, any internal analytics happening, all those. So it's not just one replica of one data being changed, but the entire series of actions, typically involving multiple systems that would have to get changed. Now, ensuring this kind of atomicity requires linkages across information systems and even possibly across organizations. For example, if every time Amazon is processing a purchase, they have to send some request to UPS to tell them to pick up a package and deliver it to such and such address, again, it requires a connection across systems. Isolation, like we talked about before, isolation means essentially that users can't peek in at intermediate stages of the process. So if you are processing some transaction that involves multiple actions, there's going to be a time where some of the actions have been updated, others haven't. If you allow users to peek in at that process, they might get a wrong indication of the state. Likewise, if you have an action that involves multiple replicas, there may be a time where some of those replicas, but not all of them, have been updated. And if you allow outside users to peek into any of those replicas, you can't necessarily control which one they're going to get. So in isolation, in this sense, we mean nobody can peek in at the intermediate state of the transaction. They have to either look in before it starts or look in after it's done. You can't peek in the middle. Now, in practice, this means there's going to be a trade-off with concurrency. You can provide isolation, but inherently, providing isolation means that you're going to restrict concurrent access, right? You're going to say, well, people can't look at the same data at the same time. They can't change the same data at the same time. If you absolutely forbid concurrency, you're going to have maximum isolation. Any concurrency you allow is going to potentially give up some of that isolation. Okay. Now, to provide isolation, what you typically see is database records will get locked to prevent overlapping operations. Okay, so once a transaction process starts, all of those records that are involved in the transaction will be temporarily unavailable to other processes, right? This prevents sort of conflicts from happening where different replicas can end up with wrong values, with different values, because people have changed them through different transactions. Okay. Once the transaction is done, either whether it succeeds or whether it fails, then the lock gets removed. If the transaction succeeds, all the replicas will be updated correctly. There's no problem. If the transaction fails, well, at least all the replicas are the same. Maybe the user tries again a little later. But either way, once the transaction is done as far as succeeding or failing, then you can unlock those records and allow other users to access them. One big problem, though, at scale, high volume or otherwise data-intensive situations can lock up the system. For example, you might have a bunch of processes that want to access the same data, or you might have one process that accesses large amounts of data. Imagine if you're going through some system, you're running a query on a large database table, and while you're looking at that, you say nobody else can access this table. Well, then everybody's got to wait. And if you have a lot of questions like that, a lot of queries running on your database like that, it can make it run very, very slow. And you might say, well, gosh, we got to allow some measure of concurrent access if we want to get any work done. Okay, so concurrency and isolation, they're both desirable of themselves. Concurrency, the ability to have multiple users access the same data and get their work done faster, that sounds good. Isolation ensures data integrity. Obviously, that's also good. But the problem is, they have their downsides. The more isolated your transactions are, that's going to limit scalability. It's going to limit the ability of your system to perform well once it gets large and there are many users trying to do some of the same things that are inevitably going to bump into each other. On the other hand, if you permit concurrency, there is potential risk that you could degrade the accuracy of your database. And this is one of those inherent conflicts. If you have isolation, you prevent concurrency. If you have concurrency, you can break isolation. So there's not really a solution. There's just options around what can potentially go wrong. Okay, so I have an article here from Oracle if you want to check that out, especially if you're an IDS person. Discuss briefly the various isolation levels. So people think about this, but unless you're a database person, you're probably not fully aware of it. It's something that's, really for experts to worry about. But it is important. Best practice, though, strict isolation for high-value transactions and concurrent access if the losses are small. So here's my link again to the Poloniex exchange. This is the big article. Let's see if that actually fires up today. Good. All right, there we are. So this is from, I don't know, 6.5 years ago. Poloniex loses 12.3% of its Bitcoins. The big hack was about $20 million worth. So if you read here, right, this bit that I'm going to highlight, the hacker discovered that if you place several withdrawals in practically the same instant, like I said, within microseconds, they get processed at about the same time, temporarily results in a negative balance, but valid insertions into the database. So the database operations are happening even though it results in a negative balance in your account. But only afterwards, only after those transactions have happened, does the system figure out, oh, wow, hey, you overdrew and we shouldn't have let you do that. Can you please give us the money back? But no, it's not going to happen. Okay, so that was a big problem. That's what happens again when you have guys that are knowledgeable about encryption and knowledgeable about all the related blockchain, but they don't know much about networking or database systems. Then hacks like that can happen. Okay, so again, strict isolation for high-value transactions, like pulling Bitcoins out of your attack. Concurrent access if potential losses are small. For example, looking at the same Facebook photo. Okay. Last thing before we get to two-phase commit, rollbacks. So a rollback is simply a recover from a transaction that fails, from an uncompleted transaction. Things like invalid transaction parameters or some sort of hardware failure during transaction, or if the user temporarily disconnects from the system, something like that is happening, then yeah, you want to restore your system to the previous good state. So the basic method that works on this, you maintain a file of all transactions that have been initiated but haven't been completed, and the state of the initial data, things like account balances, stuff like that. Anytime a failure happens, the system can be returned to its last known state by undoing all the uncompleted transactions. Now, if you're following strict isolation in your system, or reasonably strict, you shouldn't have multiple rollbacks accessing the same data. So you can just unroll them and you won't have to worry too much about the sequence, but you can restore the initial state of the system. Obviously, maintaining rollback record integrity is vital. If something goes wrong with your system and you lose a whole batch of transactions that you should have processed correctly, yeah, that is a very serious problem. Okay, so you want to maintain good rollback so that your system maintains its durability, which we talked about in the Facebook system, Facebook module. You want to have your rollback records be good, solid, up to date, all that. All right. Now we finally get to two-phase commit. So in two-phase commit, we have a basic problem. We want to ensure that two or more linked databases have the same data values after a transaction. Okay. So for example, suppose a customer is making a bank withdrawal from an ATM. At the end of it, you want to make sure that what the customer sees at the ATM itself matches whatever numbers are in the back office database. Likewise, you want to make sure whatever replicas of that account information are held by the bank are also the same values. So two correct outcomes. Either number one, the customer gets the money and all the back office databases are updated, or number two, the customer doesn't get the money. For whatever reason, the customer doesn't get the money and the back office databases should reflect that nothing changed, right? That the customer didn't get the money. All right, so that's something that hopefully makes sense. So let's get into the picture. I'm going to lift this and then I can draw it in Paint. So that will be good. I can just get to it. I don't know what we're doing here. There we go. I'm going to borrow you. Okay. So we're going to move you over into the middle. And I'm going to draw some stuff on this. All right. So this is our transaction core. Let's see what our font size here is. We can make it a little smaller. Okay. So the transaction coordinator, I wanted this in orange. There we go. Transaction coordinator, or C, is the software agent, just program running, that coordinates all the different databases involved in the transaction, right? It tells them what to do. So what will happen is user clicks buy. You got a stack of things in your basket, user clicks buy. The transaction coordinator tells all of these resource managers, get ready, we're going to do a transaction. Okay, well, what are resource managers? Resource managers, or RMs, are the software agents that control the databases themselves. Okay, things like managing replicas. All right, so if you have 3 copies of data in your system, the resource manager is going to make sure that all 3 of them get updated together, stuff like that. Okay, so what happens here, we'll go through the process. Transaction coordinator says TC tells resource managers, pencil in some changes. We are going to try this transaction. Okay, so the transaction coordinator tells the resource managers there's this transaction pending, get ready to do it, basically pencil in some changes and we'll do that. Okay, resource manager basically penciled, not literally, pencils in the changes. Specifically, checks that all replicas are available to be updated. Okay, and what else? No other problems with the transaction's validity, right? So basically everything's functional, all the replicas are ready, they can do this thing. Okay, then the prepared RMs individually respond. Let's make that a little bigger. Respond back to the transaction coordinator. Put up one saying that they are prepared. Oh, one more thing over here. I'll get that in a second. Okay, and rollback records get prepared. In case of failure. Okay, so once the resource managers are good to go, they say, okay, yeah, we're ready to go. At the end, once the TC has heard back from all resource managers, they are prepared to execute the transaction. Okay? If it doesn't hear back, if the TC doesn't hear back positively from all resource managers, the transaction will fail by timeout, right? Basically say, oh, we didn't get a response in time, we're going to cancel this transaction. So there's one of those two cases. At the end of the prepare phase, either the transaction coordinator has heard back, everything's good to go, or it hasn't heard back that everything's good to go. Or, maybe one of the resource managers says, no, we can't do this. And then the transaction coordinator will abort the transaction. Okay, so at that point, if it goes through, TC tells the RMs to commit to the transaction. Okay, basically make the changes permanent. RMs will individually make the database changes permanent. Okay. And report back to the transaction coordinator. Okay, so when done, each RM reports back accordingly. Okay, at the end of the commit phase, if all resource managers have committed to the transaction, the TC knows that everything is good and the transaction went through, and that's it, right? The transaction is through and all the databases have been coordinated, right? So there's no problem with different replicas having different values, things like that. Okay, otherwise, if the transaction coordinator doesn't hear back in time from everyone, otherwise, again, the transaction is canceled and changes will need to be undone via rollback records. Okay, need to be undone using the rollback records. So the net effect of all this right? The final result, either all databases show that the transaction happened, or all show that it did not happen. Either way, they will be consistent. And that's what we want, okay? Whatever happens, we want all of the databases in this system to reflect that it happened. Okay, we'll take a peek, see if there are any questions going on in here. How's everybody doing? Nothing in the chat? I don't see anything in the chat. Okay, does this all make sense? Any questions on this? You can answer through the chat. We're all good? Good enough? Can I go back to Notepad? Notepad, do you mean Paint? Well, it's in the video anyway. I think you mean Paint. There it is. So this will get posted up. Okay, so that's two-phase commit. Now, worth mentioning, I'm saving you a lot of time and trouble here. we look at this, I don't know why the system's being a little weird. If we look at this article, let's see if it's still here. Yeah, this is what I'm saving you from studying in two-phase commit. There's a lot of stuff here, okay? And that's just the tip of the iceberg, but that is some stuff. All right, so you don't have to read all that. You just got to understand what I did. Likewise, this is a quick walkthrough of the same thing that happens, what I just talked about in the middle. And again, if you wanted to see it, it's similar, but less detailed, but it's there as another one. Boom. Some stuff about two-phase commit mechanism, and they talk about it. That's not too bad, but yeah. So one thing down here at the end, mention the forget phase. Eventually, once the transaction has gone through, those relevant rollback records can be discarded. They won't be needed anymore. So you don't maintain them forever. I'll mention that here. Eventually, rollback records will be discarded. Okay? Because, yeah, once the transaction has successfully gone through, you don't really need to maintain that anymore. Okay. So good, that's two-phase commit. And remember, what is the basic problem? Basic problem is you have multiple linked databases. You want to make sure that they have consistent data values after a transaction. Okay. Now, the rest of this, talking about security. So, transactions inevitably contain information, could be stolen, could be misused, right? Obvious one, credit card data. You want to keep that secure. Things like the ordered items and the delivery time, right? You don't want people to come around saying, hey, that's some neat stuff that's going to be sitting on your porch, poorly guarded. I'm going to send over a truck to pick it up. The delivery address itself, and anything the customer would prefer remains private, right? So, yeah, anything like that, that's a potential security concern. So, systems like this, transaction systems, need security to avoid all the consequent costs of security failures. Things like lost goods, lost customer loyalty, legal actions, for not following accepted standard security practices. All that, companies have to be concerned about it. Another thing, fraud detection. Okay, so fraud detection is, you try to figure out, is this transaction valid? And the basic technique of that is you try to compare a particular event, one single event, to some sort of baseline historical data. For example, if a customer buys something, you look back at the customer's history and you say, is this reasonably compatible with this customer's prior purchase data? In this case, Amazon has an advantage because it has a lot more historical data about its customers. It has a lot of customers, that go back 10, 15, 20 years with Amazon, maybe 25 for a few of them. So that's a lot of historical data. But any company can use this to some extent based on standard human customer habits. For example, I remember when I bought my wife's engagement ring, we got engaged in 2010. So 10 years ago, we got engaged. We're married now, by the way. And when I went to the store to buy the ring, it threw up a big flag for my credit card. My card got frozen for a little while until I called them up and talked to them about it. But yeah, there was nothing in my past history that said I would go into a jewelry store and spend several $1,000s on a diamond ring. So it was a pretty singular event for me. Anyway, so typical classification examples, right? Number one, looking at a particular customer and their purchase history. So things like the product that got bought, how many of them got bought, what the price was, all that. Some of those could be red flags, right? So jewelry, reasonably expensive, yeah, that's not really in my history. Another obvious red flag is a delivery address, right? So if you make an unusual expensive purchase and send it to a totally new delivery address, yeah, that's probably going to throw some red flags too. There are other things that are particular product categories that are typical versus atypical of fraud. So for example, things that would be likely to be purchased fraudulently are things that are small and expensive and reasonably easy to resell. So something like jewelry, electronics, they have quite a bit of resale value, and it's not that hard to transport them. These are the sort of things that people would prefer to use for fraud. Whereas things like books or kids' toys, yeah, you might find somebody that does fraud on those, but it's hard to imagine somebody buying a van load of baby books and saying, oh yeah, I'm going to try to sell these somewhere for like 50 cents each at a garage sale. It just doesn't really make sense. It's not how fraud schemes usually work. Another thing, unusual delivery volume. So if, for example, my wife and I, when our kids still wore diapers, we bought diapers, and I don't know, we got like a box every week or something. And that was no big deal. We got on one of the subscription plans for Amazon. They regularly delivered us boxes of diapers. And yeah, in small quantities, buying diapers is not a scam that somebody's probably going to run. However, right, if you had $10,000 worth of diapers delivered to some new address, yeah, that would probably throw some red flags as well. They'd be like, wow, that's a lot of diapers, and maybe something's gone really weird here. So yeah, fraud detection, big picture though, the company's going to try to look at the transaction, say, does this make sense? Is this a high risk transaction? And they have their whole set of techniques for identifying those. Okay, so that's it for transaction stuff. We're going to spend a little bit of time talking about network architecture. So let me see, any questions on any of the stuff we've covered so far? How is everybody? Anything in the quote? Oh, congrats. Yes, thank you. Thank you. Yeah, we had our 10-year anniversary this summer, so 10 is a lot. Anyway, all right. Well, I'll move on then. So, network architecture models. So what we're looking at is how users receive and send data. And there's a few things that are going to be the same. For example, the interface is going to be on the user side, whatever it is. The user is going to type stuff into it or touch the screen, whatever. The business is going to have the database, because if the user has the database, they don't need to go through anything. But the other details are flexible, right? What applications are, where they're running. Yeah, some of those could be on the client side, some of those could be on the business side. The load could be split between the two. Yeah, the other details are flexible. So we'll talk about the two major architecture styles, client server and then end tier. And we'll start with client server. So Amazon needs this kind of network architecture that defines how customers send and receive data. Any network that's what it's for, right? It's just basically a system for regulating how data gets sent and received. So client server, it's a basic model. Clients directly obtain data that's on servers. So we'll draw a little picture. So imagine you have a server. Ta-da. Looks a little strange. I'll live with it though. And you have a few clients down here. So client 1, client 2, client 3. And they're all going to get their boxes, and okay, they have their little client machines. They're smaller. Okay, and they're all connected to the server. Wonderful. Okay. So that's client server. So the client, again, those are the end users, ordinary people like you and me. The server, in this case, okay, has data. The client has the interface. And depending how it's set up, right, application may be here, and application may be here. Depends. Okay. So the application logic might reside on the clients, might be a thick application, might reside on the servers, in which case it's thin. Now, what's some basic problems with client server model? Well, number one, there's security issues. So clients get to directly access data on the machines. They can also potentially tamper with the client application logic. That's a big one. Okay, so let's look at this. The data is here. The client has straight access to it, right? They're directly connecting to this server machine. And what can happen? I'm going to blow it up over here. What would generally happen? Whoop, I want to keep that. What would generally happen is something like this. One client would have access to a chunk of the server's memory. Another client would have access to a different chunk. Not being very cooperative. Okay. And another client would have access to yet another chunk. So he could be purple. He could be blue. Okay. They've all got their space on their machine, on the machine where their data is, right? But the problem with co-tenancy, security problem with shared access to hardware, there might be vulnerabilities where users can improperly access data. Now, if you're interested in this actually, it's not limited to client server. This actually happened in some iCloud hacks some years back. Okay, so this is a problem that doesn't go away. Anytime you have multiple users sharing space on the same data, you can say, well, a query that I'm doing should be able to access my data, like maybe there, maybe there. But what can sometimes happen is that users can specify an improper query that does some big grab of data that involves other users' data on that same hardware. So this is a persistent security problem. Now, again, it's not that common anymore, but it's still something you got to watch out for. Wait a minute. Not that common, well-known problem, but still cause for concern. Okay, it's something you got to be aware of. Okay, so that's one problem in terms of security. Is by definition in client server, these clients are going to share the same server. Second thing, difficult to scale or modify. Okay, so in the client server model, all clients share the same hardware, meaning the hardware has to run the applications and store the data for all the users. So if data massively expands, there's no way you're going to be able to store it all on one server, right? If you're talking like exabytes of data. And to access that data would require frequent switching between machines. And client server isn't really set up for that. Client server isn't set up for that, requires new rounds of login and authentication. You have to verify who you are. Okay, so that's a big problem. That's essentially why it doesn't scale very well. If all the clients are sharing the same hardware and the amount of data that's there blows up, the clients are going to have to be frequently switching back and forth between machines in a system that's not really set up for frequent switches back and forth between machines. Okay, that's the basic problem. So it's difficult to scale, difficult to modify. Sure, you can add on a few more users, but if you start running more applications, then that may change who gets assigned to which servers, may affect how well the server runs, things like that. So even changing the load on the server by changing the applications, that can be a bit of a problem for system performance as well. Okay, so here's a drawing, but my drawing is fine. We'll talk a little bit more. So if you have a small system, client server is probably okay, right? It's cheap to build and deploy. You store all your data in one point, which might actually be okay in a small system. You only have one point for patches and upgrades. That's nice. So you only have to worry about doing it in one place. And it's easier to monitor security. You just look at the one machine, verify that. You don't have to worry about things going on a whole bunch of different other machines. So for small scale, in some ways, it's an advantage. Problem is, for most systems, small scale isn't an option anymore. So client server kind of peaked in the 90s. As systems got bigger, things like Facebook and Google, they said, you know what, this basic client server stuff, this is just not going to cut it. We got to figure out a way to manage bigger systems. So problems with client server. Expansion and modification are difficult, like we talked about. In particular, the way the system performance suffers. If you're running thin client machines, right, where the work is happening on the server, as you add more users, the server is going to get slower, sludgier. it's not going to run as well. It's like if you go to some online gaming platform and it's really busy, yeah, they're just going to have a lot of people there and it's going to be busy and the system performance isn't going to be that great. Everything's going to feel like it's moving slow. On the other hand, if you have a thick client, right, if you're running all of the software on the client machines, then you have the problem where the application patching inevitably gets left to the users. So this advantage of having a single point for patches and upgrades, that falls away. Another problem, although centralized data storage sounds nice, you know where everything is, it also means there's going to be a single point of failure. So if your server fails, boom, everybody else has to go to some kind of backup machine, which could take a while. So client server in general, if you're going to have one of those systems, and they do still exist in places, it's best if it's internal to the business and away from the internet, because the internet's full of bad stuff and the internet tends to create scale problems. So yeah, if you are still running a client server, it's probably a small scale, very specialized system that you deliberately want to keep other people out of. Okay, so the N-tier architecture, N is a number typically 3 or greater, solves the problems of client server by adding some intermediate layers or tiers. And the standard architecture is 3 tiers. So I'm going to bring this up in a picture. So N-tier architecture, we'll do for N equals 3. And what we mean by a tier is just a group of machines that are doing the same kind of work. Okay, so you could have servers for data. Oh, let's just use all the same size, won't we, huh? How about that? Let's make those transparent. Okay, and then a bunch for client machines. We're gonna see if I can do this right. Okay. Yeah, nice. Okay, so over here, servers, database servers, right? Database machines. Over here, application servers. And over here, the clients. So the typical model for this N-tier architecture is to store and send data on request. Application servers primarily run applications. Okay, and the client shows up, uses the system. Okay. Now there are going to be different linkages here. At any given point, right, you might have different users connected to different machines. You might have multiple connections at the same time, for example, because any one of these application systems could require data from any of these other machines. I'm just going to draw all those connections. Let's just put them all in. Okay, so something like that you might see. Okay, so that's N-tier architecture. Now, why do we need it? Well, remember, client server wasn't scalable. It didn't perform well when the system got bigger. N-tier solves this. I was going to say mostly solves it, but it solves it well enough for what we're talking about. Solves this by allowing separate scaling of the database and the application server tiers. Okay, so one thing is you can add on different database machines. If you have a problem with too much data, you can allow a lot more. Database machines. If you are running a lot more applications or serving a lot more clients, you can provide more application servers. But they're not specifically tied to the same machine. No single machine is running the applications and storing the data, so they can be scaled separately. Number two, connections between users and system machines are much more flexible. Okay, and the basic logic here, if we draw this as the boundary of the business, let's let this blue line can be the boundary of the business. in general, once a user has logged into the system, once a user has logged in and has access, the system is less worried about that user. So internally, the system can switch connections to new machines more easily and more quickly. Okay, it's set up to do this. What would happen in practice, for example, I'll draw like an interface here. You would see something like this. There would be an interface, and the various users would connect to that interface, and then through that interface, they would be connected to one or more, all right, one of these application servers. Likewise, between the servers and the database tier, you would also have an interface, and they'd all connect through that, and they could easily switch back and forth which one they're pulling data from at any given moment. Okay, so the Anterior architecture, again, you can scale out these different tiers separately, which you can't do in client server, and the system is set up to allow users to fairly easily switch from one machine to another, which you don't have in client server. So that's what Anterior does. Now, there are systems that have more than 3 tiers. We'll talk about them in terms of running modules and applications. We'll talk about that a little bit down the road. But Anterior architecture, the basic one, is typically implemented for thin clients, so doesn't assume that there are strong machines. So you run a simplified version of the application on your own machine, but most of the work happens on application servers. So think about Facebook. You go to Facebook, you log in. There's nothing you ever had to install on your own side. You don't, install this massive Facebook application. You just show up and use what Facebook has happening in its own systems. Okay. Now the names of the tiers as well, those can change across system vendors. So depending on who you have implement your system, they might call the client tier, the presentation tier, the user tier. Your application servers might get called the application or server tier. Your database machines might get called the data or the database tier. But once you get used to the terminology, it's not that confusing because you can pretty much quickly figure out what they're talking about. Okay, so simple example there. All right. Now, another issue that's worth mentioning is tight versus loose coupling. Okay, so coupling means the degree to which system components are dependent on each other. So in a tightly coupled system, it can be highly dependent and have high performance, but a loosely coupled system means the components are fairly independent and they're easy to modify. I have an example here in the slides about movies, but one thing that I talk about that came up recently in our own house, suppose you have a thermostat, right? You have a dog's making weird noises. Hey dog, you okay? All right. He's having weird dreams. Okay. So we had a thermostat in our house. And the neat thing about a thermostat is you can take a standard one off, right? I'm going to just go ahead and make a whole new picture. I'm going to get rid of this and then I can restore it in a minute. Neat thing about a thermostat, this is a thermostat. It connects to some electronics down in the furnace, the boiler, whatever, okay? So we'll call this the actual temperature change producing machinery, okay, whatever that may be. Your thermostat's going to send a signal to it, and the temperature changing producing machinery is going to respond correctly, right? So the thermostat, update temperature, and the machinery does it. Now, neat thing about a thermostat we get to, if we have a different one, say, oh, you know what, this thermostat fails, I'm going to replace it with some other one. So we have our replacement thermostat. The neat thing about this is we can probably just swap it over, right? We can probably just say, okay, I'm going to take out this one. I'm going to draw a big red X over this one because this one's gone. Okay, I could just pull that thermostat off the wall, buy a new one that's a standard kind, put it in there, and it'll work the same way. It's not necessarily completely tied to the temperature change producing machinery. Okay, so in a tightly coupled system, the thermostat would be inherently specified for the machinery. I could only replace it with identical hardware. Okay, so if something goes wrong with this first thermostat, in a tightly coupled system, yeah, I have to know that this system is going to be communicating the same way with this. Or more generally, I can replace the thermostat if I know how the machinery works and that the thermostat is compatible with it. Okay, so I have to peek in there and say, oh, this thermostat works this way. The machinery expects this kind of electrical signal to travel down the wire. If that's compatible, then that's fine. Okay, and this knowledge can allow optimizing the operations in various ways. Okay, it can allow optimizing the operations because the thermostat can take advantage of machine specific capabilities. So if there's something special about my machinery, then this kind of tightly coupled system, the thermostat can be designed specifically to take advantage of those, right? For example, like a piece of smart hardware that is only going to do these temperature changes if there's somebody actually in the house that can notice them, right? It could be something like that. However, loosely coupled system, a loosely coupled system, I don't need to know how the machinery works. I just need to get a standardized piece of compatible hardware. Okay, basically, as long as it sends correct output to the machinery, it can work. But I generally give up the ability to take advantage of all the machine-specific capabilities, right? So I can buy a generic cheap thermostat that can still regulate the temperature, but if there's something special that this machinery can do, that generic thermostat might not be able to do it, okay? It can still regulate the temperature, but maybe it can't do everything that the machinery is capable of. So this is the trade-off, essentially. Tightly coupled, higher performance, but harder to modify. Because if I'm going to put in a new piece of hardware for the thermostat, not just a replacement of the same kind, but a new one, I have to do a lot of figuring out to see if it's going to be compatible. I might have to tweak that hardware somehow to make sure it is, whatever. Loosely coupled, lower performance, but lower requirements for mods, right? So if I want to change something, yeah, I'm not going to have all this detailed stuff about the machinery, but the basic stuff, yeah, it's going to work and it's easy to manage. So that's the essential trade-off. So as far as network systems, right, if you had a tightly coupled system, the components are going to be designed and integrated with all sorts of knowledge of what hardware is being used, what software is running, what communication protocols are being used. And you could do basically the best you can. You could design the best possible system with that hardware, software, everything. But the problem is if any of those change, right, if there's a new version of the hardware that comes out, or if there's some tweak to the communication protocol, that might affect a whole bunch of things in the system. And you have to analyze the whole system to make sure that problems aren't going to happen. On the other hand, if you have a loosely coupled system, communication is going to happen through standard interfaces. The different hardware and software aren't specified for particular machines, right? They're sort of general applications. So as long as the hardware and software conform to the interface, there can be flexibility there. So system is easier to change, but the performance is going to be suffered. You can't closely coordinate everything and make sure it's working as well as it possibly could. Another simple example, operating systems. So operating systems are specified for a particular category of machines, right? So you have a somewhat tightly coupled software there. So your Mac OS is specified for Mac machines. Your Windows is specified for Windows machines. On the other hand, generic applications, like you go to a web app and you go to some web page like slither.io, if you haven't seen that, you go there and any machine can log on and play it because it's running in a browser. As long as your machine can run a browser, you can run that application. It's loosely coupled. Okay. So, advantages of Anterior architecture. Number one, it's generally easier to maintain. The system components are modular, and they're also generally isolated. So if you change one part of the system, it doesn't directly affect others. So what I had here, when I said your different clients, they might access the application tier through a shared interface. Okay, it could be something like that. Yeah, then what happens? Well, if I change one of these machines or I add on extra machines, all I have to do is make sure there's capacity in this interface for it, right? It's not going to, if I change this machine, it's not going to directly affect what these two other ones are doing. So that's a nice thing. Likewise, if I make some changes in the database tier, it's not going to affect directly what the application servers are doing. Contrast that with client server. If you have all the applications and all the data stored on the same machine, yeah, changing the data could affect what applications you can run. Changing the applications is going to affect what data you need to get stored locally. It's a harder decision to make and to get the system to perform well. Okay. In terms of security and reliability, well, the application logic still remains internal to the business. Nice thing, data gets accessed through standard interfaces. So, because when you're launching a query through this kind of system, make it a little clearer here, the query not only has to get to the database machine and run correctly, it has to be correctly processed through the application server and not recognized as something bad. So basically, you have to go through an extra round of checks in order to access something that you shouldn't be able to access. So security is going to be a little bit better. You don't have to worry about those sort of co-tenancy issues generally. Okay, and in general, it's also much easier to test the system. Because why? Because it's more flexible. Client server, right, you have to be pretty sure that the conditions you're testing on are also the conditions that the system is going to be running on. So if your system stays static and you don't have that many users changing and you don't have that many application changes and the data doesn't change that much, yeah, you can test client server pretty well. But again, once those things start becoming more fluid, then the testing is going to be a lot tougher. On the other hand, with this kind of N-tier architecture, even if you get a little bit extra load on one of these machines, well, you can always expand it out. You can scale out that tier and manage system performance that way. So testing is going to be a little bit easier because even if something goes wrong, you can manage it easier. The other thing is you can isolate portions of the system and test them in isolation. It's hard to do for client server. Okay, scalability. The tiers can be scaled independently, so if you need to add more data or more clients, that's easy. And the fact that everything is already designed in a modular way makes it easier to transfer components to the cloud. So for example, if you want to keep the applications running on your premises, but you want to send data to the cloud because you don't want to deal with that kind of issue, Yeah, you can maintain all of this internally and put the data on some remote system. Or if you want to just send the applications to run in the cloud but keep the data on premises, you can do that too. Okay, so it's easier to manage. Client server, you can't really break those features up. You could put the entire, machine in the cloud if you wanted to make a replica of that, but yeah, that creates its own set of problems we'll talk about eventually when we talk about cloud. Okay. Anyway, integrating networks and systems. So customers, of course, aren't the only users of Amazon's transaction processing systems. You have a lot of other groups doing operations with each transaction, things like payment verification and fraud detection, warehousing systems, any contacts with a third-party supplier, shipping, which again could be internal to Amazon, or it could be outside people like FedEx, UPS, USPS, and they have to have their systems interfaced with Amazon's as well because they have to exchange notifications. Okay, so let's talk about object description languages because that's the core of these kind of messages. So, for example, suppose somebody orders a set of goods from Amazon, and we want to construct an object so we can send it through a standard interface. So remember, we were talking about tight versus loose coupling. We want to set up our system so it's not super tightly coupled. So it's not designed for a particular transaction type, but can handle any reasonable transaction. So as long as the transaction contents are formatted correctly, we can send it to any system. We can send it to FedEx, UPS, whoever. Okay. So to do that, you need something called a standard object format. So an object is just going to be a set of data that represents something. And if you have a standard format for it, then you know that you can send out some object, whatever it is, whoever receives that message will be able to process it correctly. So an invoice for one box of diapers, it's basically going to look the same, get processed the same. It's an invoice for 10 refrigerators. The object format is just going to be a list of 10 refrigerators. Whoever gets that, they'll know what the contents of the delivery are. They'll know how to process it. Okay. So on Amazon, whenever you place an order, what's going to happen is this invoice object gets built from the ordered items, and then you wrap around some metadata. So metadata is data about the data, data that describes the data. So here's our example. You have Joe Snow. Joe Snow orders a few things. He orders a red hat, yellow shirt, blue pants, and a hardcover copy of Green Eggs and Ham, and has it delivered to 456 Igloo Circle. Okay? So that's the invoice. That's all the stuff. Now, you could arrange this in a lot of different plausible ways, but one way that humans might do it, we'd list the customer, we'd list the address. Here we have some metadata mentioning that the address is in the US format. We have the item count being 4, and then again, that 4 is a metadata. The fact that there are 4 things in the order, that's data about the data. And then the items themselves, right? The list of 4 things: the hat, the shirt, the pants, and the book with some descriptive text afterward. Okay, so there's two widely seen ways to do this. One is something called Extended Markup Language, or XML. So XML is a general purpose object description language. It looks like HTML, which is the language of web pages. We'll cover that eventually. And it's in decline, but it is still used. If you have a big old system full of a lot of data and nobody's ever gotten around to converting their XML to something more current, yeah, you still see it. So why did XML become obsolete? Well, number one, the text in it is relatively bulky. It has these tags I'll show in a second to open and close attributes, and those take up space, and if they take up space, they take data. And if they take up data, it's going to take longer to transfer that data from one point to another, longer to process it generally. Number two, XML doesn't inherently display correctly on a web page. Okay, you have to design a browser that specifically formats things the way you want them to be displayed. So if you're going to display things in XML, you're going to have to do some kind of conversion or specification for the web page that you're showing it in. Number three, if you have arrays, arrays are not automatically handled by XML. So an array is a stack of data of the same type. So for example here, we have 4 items. In XML, you have just a list of those items, but those items aren't inherently numbered. You have to have some mechanism in your system for counting which of those items you're referencing. And it's often hard to read, although your mileage may vary. It depends. But most people who look at XML versus JSON, we'll see in a minute, say, yeah, JSON is easier to see. Okay, so here's how things look in XML. So for example, we have this. This is the invoice tag. This is the opening tag. This is the closing tag. So that's the entire invoice. And then within the invoice, we have our various elements. So here we have customer, and the customer has the attribute first name, Joe, and then the end of the first name, and then he has the last name, Snow, and then the end of the last name, and that closes out customer. Now, if you look at how much text there is involved here, the only data that we have is Joe Snow. We literally have just 7 characters of text. But how much is there in terms of tags just around that? Well, we have 8 characters for customer, another 11 characters for first name, 12 characters to close out first name, 10 characters to open last name, 11 characters to close out last name, and 11 characters to close out customer. So more than 60 characters of padding to enclose 7 characters of text, right? So when I say it's bulky, that's what I mean by saying it's bulky. Similarly, right, we have a tag for address, so there's a number, there's a street. We have tags for the item. Each item has a category and has a color as attributes. And then that's the end of the items list, and then the end of the invoice. So XML looks like this. When we see HTML a little later on, HTML has these same kind of tags, but it's pretty bulky. Now, the other one is JSON. JSON stands for JavaScript Object Notation. So JavaScript is a language used for providing dynamic content on web pages. We'll talk about that towards the end of the course as well. So it's a different notation style based on JavaScript. Nice thing is it can be read directly by JavaScript engines and standard web browsers. It's currently the widely used one, widely used object description language, although some people have come up with competitors, nothing has quite caught on. For example, Google had one. They had a next generation object description language. They were hoping it was going to dethrone JSON. It still has its uses. Some people use it, but no, in general, JSON is still the popular one. The 2 big advantages of XML, number one, it's a lot more compact. So it doesn't have the double tags. It basically has an opening tag, and then for closing it does a bracket, so a single character. So less data storage required means less time for delivery, less time searching through the data to find what you're looking for. And number 2, because it's automatically compatible with JavaScript, you don't have to do any conversion or parsing to display it on a web page. And it'll automatically be compatible with whatever you're doing in JavaScript on your web page. Okay, so example of how JSON looks. So for our invoice, we have the attribute customer. Customer has an attribute first name with Joe and then a last name Snow. Okay, so we have the opening tag still. We have first name and last name, but we don't have the big closing tag. So basically, the amount of data required to hold the tags is about cut in half. Okay, second thing, these square brackets here, see the square ones? Those are array boundaries. So in JavaScript, for example, if we're displaying an invoice on a web page and we have this list of things, they're automatically going to be numbered when any JavaScript code is referencing them. So I can automatically set up features like I can put buttons next to these items, and when I click on that button, I don't have to do any special parsing. I'll just know, oh, reference item number, the first item in this list, or reference the second item when I click the button that corresponds to it. It's much easier to automatically generate code to somehow interact with these object contents. Okay, that's it. So what are our key takeaways today? Well, we learned a few things, right? 2-phase commit, you should understand what it is, how it works, why it's important. Transaction security, understand some of the things there. I mean, that's mostly common sense, but still worth thinking about. Same for fraud detection. The 2 network architecture models, talked about client server and talked about end tier, know their advantages, know their disadvantages, right? And then tight versus loose coupling, should understand what that is. And object formats, right? So basically, what's XML, what's JSON, how are they different? Why is JSON more popular than XML? That's about it. Okay. So client server, yeah, client, oh, we have a last question here that I didn't get. Is client server just good for small scale? Yeah, good for that. Good for small scale. And also good for very private systems. Okay. If you specifically don't want people switching between machines, then client server makes sense there as well. You install the applications, you have that data on that machine. Only the people who can, sit down at a workstation and directly access that machine are going to have access to it. Okay, so ironically, although client server is often not better in terms of security, client server probably is the appropriate selection for a super secure system. Okay. Well, I'm going to start recording, but if people have any questions, I'm going to stick around for a minute.